the input arbitrary signal x of n, input arbitrary is nothing but it can take the any value it can take here, arbi tar arbitrary signal. Let us consider input arbitrary signal x of n, okay, as shown below. So what I am going to do is, okay, so sometimes okay, so it is not visible because in another network the data has been emptied. Okay, so now I am using this one. Okay, so another phone I am using. So okay, so here I'm going to consider the input signal x of n. I'm going to consider here input signal x of n here. So this input signal x of n will be taken in the form like this here. Okay, so you know input, it's a discrete time signal. So the x of n can take the value something like this here. So some randomly I'm going to consider the some values I'm going to consider here. Okay, so like this randomly I'm going to consider. So this is a thing about 10. So in the negative axis also some values will be there. So this is say something called x of 0 or 10 is equal to 0, n is equal to 1, 2, 3, 4, 5 and so on here. So this is -1, -2, -3. So this value I'm going to call it as x of 0, and this value at 10 is equal to 1 I'm going to call it as the x of 1. I'm going to call here x of 1. At this one I'm going to call it as the x of 2, and this one x of 3, x of 4. Okay, so this is x of -1, x of -2, x of -3 and so on we are going to consider here. Okay, and so on we are going to consider here the input signals, the x of 0, x of 1, x of 2, x of 3, x of 4, something like this we are going to consider here. Okay, so these are input signal we are going to consider. Done, right? Okay, fine. So now what I'm going to do is I'm going to express this input signal as a summation. I'm going to express here as a summation. I'm going to express here. So this is at x is equal to n is equal to 0, n is equal to 1, n is equal to 2 and 3 here. So I'm going to use this one. I'm going to express this one as a summation. I'm going to express here. So how I'm going to express as a summation is, okay, so this is x of at n is equal to 0. I can multiply this one with the delta of 0 here. So delta of 0 I can multiply here, delta of 0. So where I can express as the time delayed sequence I can express here. So delta of 0. So this one I can express as a, so delta of something called n minus 1 here, because these are 10 is equal to 1. These are 10 is equal to 1. So I can represent as a delta of n minus 1. So this I can represent as delta of n. And this one at n is equal to 2, I can express as a product of delta of n minus 2. If I substitute n is equal to 2, I'll get here. So this one as a product of delta of n minus 3. Okay, so this as a product of delta of n minus 4, because multiplying one with any sequences will remain the same thing will be there here. Will remain the same thing will be there. So that's why I'm going to multiply this one with the delta impulse function here. Okay, so similarly this one I'm going to multiply with the delta of n plus 1. So this one I'm going to multiply with the delta of n plus 2, delta of n plus 3. So like that we are going to multiply here. Okay, so like this we are going to multiply with the corresponding signals we are going to multiply here. So you can take here. So this is delta of n at n is equal to 0. So this is delta of n minus 1 at n is equal to 1 here. This is delta of n minus 2 at n is equal to 2, n minus 3 at n is equal to 3, n minus 4 and so on we can make use here. So right, and so on we can make use of this sequence. Everyone has taken note? Okay, so like this we are going to express here. Why I'm expressing is because I need to derive the convolution, some formula I need to define here. That's why here. So I think everyone has taken this one. Okay, so done. Okay, fine. We can take. So so we are going to express this input as a, we are going to make it as a sum of the delayed functions we are going to take here. So you can take, let the input is made up of, let the input is made up of a delayed impulse functions, impulses you can take here, impulses having different amplitudes, okay, mathematically can be defined as mathematically x of n can be defined as So I'm going to define the x of n. This x of n I'm going to define mathematically. I'm going to define as the sum of these things here, because whenever it is there, we can express this one as sum. We can express here. So like this. So x of n is equal to the, so it, from the minus infinity up to some minus 3, I can take dots. I can represent here. So this is x of minus 3. So 10 is equal to minus 3 here. So I can express as the product of delta of n plus 3 plus 10 is equal to minus 2. So x of minus 2 into delta of n plus 2. 10 is equal to minus 1. So x of minus 1 into delta of n plus 1. Okay, 10 is equal to 0. I can express as x of 0 into delta of n here. 10 is equal to 1. So x of 1 into delta of n minus 1. Okay, so x of 2 into delta of n minus 2. And so on we can express here. And so on we can express the sequences here. So like this we can express the input sequence x of n, we can represent like this here. Okay, so x of n, x of minus 3 into delta of n plus 3, x of minus 2 into delta of n plus 2. So this is the summation we can represent here. So while I am using the sum here, so this does not mean that I'm adding the signal x of minus 3 with the x of minus 2 and so on here. So it is just a summation I'm going to represent. We can't add like that. Why? Because this is defined at delta of n plus 3 here. If I'm going to convert this into the normal representation, so the signal will become like this here. If I'm going to represent in the normal representation, the signal will become like this. So x of minus 3, comma, x of minus 2. If I remove the term called delta, so this will become like this: x of 0, x of 1, x of 2, and so on here. Okay, so the sequence will become like this here. If I'm going to remove the impulse function, if the impulse function is there, we can represent with the plus summation. We can represent here plus. Already we have seen on problems in the elementary signals how to represent the signal here. So right. Okay, so now instead of writing these terms, many summations, many sums. Okay, I'm introduce the summation I'm going to introduce here, which is going to take the values from minus infinity up to the plus infinity, minus infinity up to the plus infinity. So we can write that one as x of n is equal to the, I'm introducing one variable called k, that k can take the value from minus infinity to the plus infinity. So x of k, okay, into delta of n minus k here, x of k into delta of n minus k. So I'm going to take here x of k into delta of n minus n. If I substitute k is equal to 0, it has become x of 0 into delta of n will get here x of 0 into delta of n. If I substitute n, k is equal to 1, it has become x of 1 into delta of n minus 1, it will become here. If I substitute k is equal to 2, x of 2 into delta of n minus 2 will get like this here. Okay, so done that. I'm going to introduce a term called k summation. I'm going to introduce here. Okay, so done. Okay, so now for this input, I'm going to give as a input for the LTI system. I'm going to give here. So this x of n I'm giving as an input here, and we are going to find the output here. Okay, we are going to find the output of the system here. So you can take the response of the system, the response of the take the next line here, the response of the LTI system for the arbitrary input, ARBITARY, arbitrary input x of n is given by okay, x of n is given by, so the output is nothing but y of n here. So this y of n is equal to h of x of n we are going to get here, h of x of n here. Okay, so that is the output we are going to get here. So that is y of n is equal to h of x of n here. Y of n is equal to h of x of n. We are going to get the output here. Okay, so that is the output we are going to get here. Y of n is equal to h of x of n here. So now in place of x of n, I'm going to substitute the expression summation, whatever we got the summation here. So this summation I'm going to substitute in place of the x of n here. Okay, in place of the x of n, I'm going to substitute the summation here. So you can take y of n is equal to, you can take substituting for x of n, substituting for x of n. So if you're going to substitute here, so y of n is equal to h of, okay, so the summation k is equal to minus infinity to the plus infinity x of k into delta of n minus k here. x of k into delta of n minus k. So you are going to get here. Okay. X of k into delta of n minus k. So right now, what you are going to do is I'm going to apply the property of the linearity and time invariance. I'm going to apply here. So linearity is the thing, but it is going to satisfy the two property. One is called as scaling property, other one is called as a summation property, superposition property here. Okay, so you're going to call that one as a homogeneity property, other one is called as a scaling property. You're going to call here. So that superposition property and homogeneity property. Okay, so these two properties I'm going to apply. That is called as a linearity. Other one is called time invariance here. Time invariance is the thing, but the shift in the time shift in the input signal results in the identical time shift in the output signal. So that one you're going to apply here. Okay, so you can note down that thing here. So now I'm applying the operator, system operator H for the system here. So the system is going to operate for the input sequence, which is in terms of the n. It is going to operate here, which is in terms of the n here, because the output is y of n. So the system is going to operate on the terms which is in terms of the n here. Okay, so since x of k is there, we are going to treat this x of k as a constant. We are going to treat. Why? Because it's not a function of n here. It is not a function of n. Okay, we are going to treat this one as a constant here, and delta of n minus k. So n is present here. So for this one, you're going to apply the property of linearity and time invariance. You're going to apply here. Okay, so you can take, since x of k is a function of k, since x of k is a function of k and can be treated as constant Okay, so now you can take, applying the linearity property, So if you're going to apply the linearity property, so the property can be applicable like this. So y of n is equal to, since we are going to treat x of k as a constant here, summation k is equal to minus infinity to plus infinity. So x of k will remain same thing. So h of delta of n minus k. Okay, so delta of h of n minus k will get here. Okay. Okay, so now what I'm going to do is, so this h is the thing at the system operator here. For example, if I'm going to take h of delta of n, if I'm going to take here, so this is the concept of linearity I am applied here. Okay, so h of delta of n is the thing, but we can call this one as the h of n you're going to call here. For the system, I'm giving the input as the delta of n I'm going to give. Whatever the output you're going to obtain, that one is the impulse response you're going to call, that is called as the h of n. So this is called as the impulse response you're going to call here. So I've given the definition of the impulse response here in the beginning. Okay, so for the system, this is a LTI system. Delta of n is the input I am giving here, and output you're going to obtain as h of n, and that one you're going to call it as a impulse response. You're going to call here impulse response. Okay, so done, right? Impulse response you're going to call here the output of the system, and by applying the time invariance property here. So apply time invariance property. So time invariance is nothing but time invariance property. So apply the time invariance property. So applying the time invariance property. So time invariance is nothing but what? The shift in the input signal results in the output, identical time shift in the output signal here. So h is there. So delta of n is the input signal. We got the output as the h of n here. Suppose if the input is shifted by the time called h of delta of n minus k, then output is also going to be shifted by a h of n minus k we are going to obtain here. So this is called as a time invariance property we're going to call here, time invariance property. Okay, so applying the time invariance property. So you got it now? So it's visible. Yeah. Apply the time invariance property. So h of delta of n minus k is equal to the h of n minus k will get here. H of n minus k. This is called the time invariance property we are going to apply. Then by using substituting this one here, so you're going to get y of n is equal to summation k is equal to minus infinity to plus infinity x of k into h of n minus k will get here, h of n minus k. So this in term you're going to call it as a x of n convolution with h of n here. Okay, so y of n is equal to x of n convolution with h of n. So here this star operator is called as a convolution operator we are going to call here. So convolution operator we are going to call here. convolution operator. Okay, so it is going to satisfy the commutative property. It is going to satisfy here commutative property. Okay, so you can take y of n is equal to the summation x of k into h of n minus k. So that is x of n convolution with the h of n. Okay, so it is going to, this is called as a convolution operation. We are going to call here convolution operator. So right, convolution operator. So it is going to satisfy the commutative property. You can take convolution satisfies the commutative property. Convolution satisfies the commutative property. Commutative property. So commutative property is nothing but, so y of n is equal to h of n convolution with x of n. X of n, that is nothing but, so we can have the shift in the, x of k. So that is h of k into x of n minus k. We can have the shift here. Okay. So this is the convolution property. It is going to be commutative property. It is going to satisfy here. Okay, so done, right? So this is a convolution operator and commutative property. So here the convolution is nothing but, so in the convolution what we are going to do is we are going to shift the one sequence. You are going to shift here. So n minus k is nothing but shifting of the one sequence. Other sequence you are going to keep constant here, and we are going to multiply, and addition we are going to do it here. So the summation is nothing but addition, and this is nothing but multiplication here. So convolution is nothing but, it's a consists of the three operators, three operations. One is shifting of the signal, other one is, okay, multiplication of the signal, other one is addition of the signals here. So that together constitute that all three together will constitute the convolution sum. It is going to constitute here convolution here. Okay, so this convolution satisfies the commutative property. Either we can take in the, any way we can take the convolution, we can take here. So right. Okay, so here we are going to use the convolution. We are going to use in order to find the response of the LTI system. Okay, so this is the LTI system. This is the LTI system here. For the LTI system, in order to find out the output, we are going to use the convolution here. So the convolution is the thing, but it is going to take the convolution of the x of n with the impulse response h of n. It is going to take that one. You are going to call it as a convolution. We are going to call here. Okay, so you can take the above equation represents the above equation. The above equation represents the above equation represents the above equation represents the convolution of the input sequence. Convolution of the input sequence x of n with the impulse response h of n of a LTI system. The above equation represents the convolution of the input sequence x of n with the impulse response h of n of the LTI system. Okay, so you can ask what are the applications of this convolution. You can ask here where we are going to use this one here. As I told earlier, so in order to find the output of any system, okay, any system is, for example, I'm going to design the filter. So that filter will be having the filter coefficients called h of n. I'm going to design here. So in order to find the output, okay, if I want to find out the filtered sequence, I need to take the convolution of the input signal with the filter coefficient, whichever we are going to define here. Okay, so that is the application of this one here. We are going to have the application we'll see in the next semester in the digital signal processing. So there we are going to design the filter coefficients, and we'll see the application of this one here. Okay, so now this is a convolution sum we have seen here. So now already we have seen the impulse function we have seen. So for the impulse function we have seen many properties we have seen. One is called as the product property we have seen for the impulse functions. Okay, so product property is nothing but, so we have seen the x of k with the delta of n minus k. Okay, so the product properties we have seen, that is x of n into delta of n minus k, and also the shifting property we have seen. So time shifting property we have seen here. So one more property called the convolution property of the impulse function is there. So you can take the convolution of the, so this is very, very important here. The convolution of the of the impulse functions. Impulse function is given by the convolution of the impulse function is given by. Okay, the convolution of the impulse function is given by. Suppose if I'm having the impulse function, say delta of n, okay, convolution with the other function which is called as a delta of n minus m, n minus m. So we can write that one as a delta of n. Okay, so minus m we can write here. Delta of n minus m we can write here. Okay, this is the one kind of property. The other kind of property is delta of n minus m convolution with delta of n minus k. So here, so delta of n convolution with delta of n is delta of n. Okay, minus. So here minus is common here. So we can take this as a m plus k. We can take here. Means we can add or take on the difference of these sequences we can take here. Okay. So similarly, the different versions I am going to write here for the impulse function. So delta of n plus k. Okay. So here I'm going to take the n. Okay, I'm going to take the minus common. I'm going to take here. If I take the minus common, this will become m minus k. Okay, so at the last delta of n convolution is the delta of n. So this is nothing but delta of n will get here. Okay, so these are some different versions of the convolution property of the impulse functions here. Means if the two delayed functions are there, I can take the sum of the delay. For example, delta of n minus 1 convolution with delta of n minus 2. I can write straight away as delta of n minus 3. I can write here. Delta of n minus 3 I can write here. So if I'm having delta of n minus 1 convolution with delta of n plus 2, so I can write that one as a delta of n. Okay, minus 1 plus 2 will become, so it will become plus 1 here. So delta of n plus 1 you can write here. So examples I'll write here. So delta of n minus 1 convolution with delta of n minus 2. So this I can write as delta of n minus, if I take the minus common here, so 2 plus 1. So delta will become delta of n minus 3. So similarly, delta of n minus 1 convolution with the delta of n plus 2. So this has become delta of n minus. Okay, so 1 minus 2. So this has become delta of n plus 1 will become here. So another one is delta of n convolution with delta of n. So this will become delta of n will become here. So these are some examples we will take here. So because this will be useful in order to find the